also another vector B that is rotating, etc. You might have all kinds of vectors. So in that incidence, if we asked ourselves, what is the circulation of this vector B through this closed path? Notice what I'm saying. I think I needed to delete this. And then I say that I do the different color. I say that this is my path. This is closed path. And this is my vector B. It is rotating in that direction. So what looks like from this idea is that my vector is rotating along the same closed path. And therefore, when we look at what we said is that the circulation is from point A to point B, sorry, of vector A, okay, now I'm calling it vector B, dot, we said the magnitude, sorry, we said that the circulation is obtained by the magnitude of vector B cos theta, of course, with along the length dr. So that is, I hope I'm not confusing you. I'm trying my best not confusing you. So we are saying that this is vector B rotating along the direction shown. And then this is my cross path R. If we ask ourselves, what is the circulation of B along path from point A? I can call this point A and this point B. So how much circulation is the vector B making? All I have to do is what we define in the line integral, and we say that is given by B magnitude, then cos theta, the angle that this rotation makes with this curve, and we can see that we can assume that this angle, they are not making any angle. Therefore, that angle is actually 0. Therefore, when we know cos of 0 is 1, therefore it is going to be simply the magnitude of B. That is the idea that I'm trying to repeat here. So having said that, now that was purely for illustration. Let's now do our example that we have right here. Hope I'm not going to delete what I not have deleted. Yeah, I think here we are. Some things I've deleted, but let me wrap this one as well. So we have, this is our path that is defined by 1. This is our path that is defined by 1, 2, 3, and back to 4. And as you can see, that is a closed path. That's a closed path, and that is the one we are defining as the closed integral R, meaning that it is a closed path. That is number 1. So what we need to do is to integrate our vector that we have defined above here, F, with respect to that closed path. And that is the one that we are defining at this stage. So we are saying that it is going to be F dr, and this can be broken into 4 paths: path 1, path 2, path 3, and path 4. And that is the integral that we are doing. So having said that, so how do we perform that integral? I have tried to break it down as much as possible here for us so that we can see how we are going to do that. Remember what we said, and again, I have to remind you over and over again, that this is equivalent to, you get the x component, fx, just a minute. So sorry for that. So we are simply, when we do the dot, remember what we said, that if you have the x component ax, it has the unit component vector a that. Therefore, when we are doing dl dot dl, we are supposed to get the dl also has the ax dx plus all those. Therefore, what we do is that you dot with ax and then dl. And if you remember what we said in our definition, we say that ax dot ax is equals to 1. So this is the one of the axioms that we defined about the dot product, and therefore we are going to apply it here. So when we do that, we are going to have the following: that when we want to do the integral over the first curve, and I won't take you there now. Anytime I add some material that is new, I have to delete it so that my screen remains clear. So what we are doing is the following: we want to understand this path 1 here. And you can see that this path 1 has only one component, which is ax component. And the ax is varying from, 1, it was at this point, to 0. So that is why we have 1 to 0. Okay, and then our fx, we can always break our f, a vector, into the fx ax plus fy ay plus fz az. And since we were given f area, so the term with the x component is my fx. The term with y component is my fy. And the term with the z component, or the unit component, okay, the unit vector is the fz. So we are saying that we are going to do fx dot ax, that point, then dx. So going down here, I'm trying to, as much as possible, not confuse you, is that my fx is x squared. I hope that is straightforward. My fx is this x squared. And therefore, we are going to get that x squared we're going to get this x squared. This is now my fx. And then because we know that ax dot ax has become 1, we remove it, and now we are left with dx. So we are going to be doing the integral of from 1, this one, to 0, this one, to 0 here, then over the integral. And then that becomes the obvious integral that we know, which is x squared dx. When you integrate, becomes x cubed over 3, and with the limits given becomes -1 over 3. So that is the first path between along path 1. And then for segment 2, we can see, which is the important point we need to identify, that x is equals to path 2. Look at this path 2. I'm keeping on laughing so that you see. My path 2 is the one that is indicated there. So we can see that along path 2, the x component is actually at point 0, the where we stopped. So x at that point is 0. What about z? Z has not gone up. Z is the one that goes up. And since we have not gone up, therefore z is also equals to 0. So from that point, we can definitely say that from f, which was defined as that, okay, I think I can follow this that I had worked on here, which is rather the same. So remember here we are doing fy dot ay gives us, this is the second path 2, and therefore we just need to pick the path ay here, which is this one. The others, the x and the z are 0, and therefore what that gives us is that we are going to be integrating negative x z. We're going to be integrating negative xz from y is 0 to y is 1, and with respect to y. And that becomes again a normal or a typical integration that you can do with respect to y. The only term that we introduce here after the integration is that it will become where is it? It will become x, y, z. And that is what I think I have here. It will become this term, x, y, z, and y is varying from 0 to 1. When you do that, you just replace y, of course, with respect to these two limits, what you'll get is it becomes minus x minus z. And I am trying to bring them here. So the first term that we did, and I think we have done that with you, is that we obtained that through the first part, it became minus 1 over 3. And when you do the second integration, we have found that the limits are from 1 to 0, which is minus x, z, y, and you have been replaced y becomes a 1. So, but we have already seen earlier that at that point, z is equals to x is equals to 0. Therefore, this term or the integration along the second path becomes 0. That is why I'm indicating here that this is 0. And again, that is quite clear because we have said here that z and x are 0. Therefore, when you replace 0 in this equation, which has x and z, you just get 0, and this term becomes 0. We are saying that the integral term for the first path is minus 1 over 3. The second path gives you the 0, and that's where we are here. Just followed a different method. I followed my own method. So we have found those two terms, and now you can do for the path 3. And for the path 3, all you need to know is the following. I'm going to wrap again. This becomes my path 3. I think I keep on grabbing my board. So this is my path 3. Of course, times you work with arrows so that in case there is something that is you cannot see my pen, you can always know the one I'm pointing at. So this is the path 3. And now it is not as straightforward as path 1 and path 2. So what we are saying is that at this point, we can start by identifying what are the constant terms. And you can see what I have put here is that in this plane, y is not changing, y is constant. Y is remaining at what? Y is remaining at 1 at that plane, because you can see we stopped at y at that point, but y is not changing anymore because we're not going towards this direction or that direction. So y remains at 1. So what we definitely do therefore is we say that for the path 3, y remains at 1. And we are going now to be differentiating with respect to the two terms, which is dx and dz. Now that we know what our fx was, remember what our fx was? Oh, sorry, not fx. Our f was this one. So the first thing that you do in this case is to replace y with 1. So what you'll have is that this term becomes 1, and I think that is the only term that becomes 1. So now my f will come down here as x squared minus xz minus 1. And that is what we have here. So here, remember you had y squared became 1. And therefore we are left without in y term in that case. Therefore, we have said that my DL will have only 2 terms, dx and dz. And therefore, when you do this dot product, you are going to end up with what? Let's see that, because it may not be very straightforward. So we are saying that when we dot product this term with this term, we are simply saying that AX will dot with that and AY will be lost because it is not there. We don't have AY term, and therefore it is going to get lost. So we are going to be left with this term and this term. That is why we have x squared minus 1. Of course, x squared you dot with AX becomes dx. Let me grab x squared becomes dx, then minus this one 1 dx. So when you do that, it actually gives not dx, rather dz. Just to be sure that I don't confuse you further, we have done the dot product. The dot product gives you dx where there was ax, and 1 dz where was the az. But now there is something else that we are coming up with that is very unique that we must all get. And we are saying so we are here. I have illustrated how we are getting this. And in case you have any problem, you can always ask, because you're doing this one is not there because we don't have the AY product. You do the dot of this and that, it becomes x squared dx. And then you have the dot of this becomes minus 1 dz, comes that. And therefore, we are at that point saying this very important concept that will not be straightforward, that the rate of change of x is the same as the rate of change of y, because we are saying that this is 1 and this is 1. And therefore, the rate of change of x is the same as the rate of change of z. So that is a very important term that we must adopt, that z is equals to x. And therefore, we are adopting a new term here that dx is equals to dz. That is not straightforward. You need to capture that. So if that be the case, therefore, we can replace one of the, we can replace x or z with, or okay, we can replace z with x or x with z. But if we opt now to replace z with x, we are simply going to end up with this x minus 1 dx. We have simply replaced this with dx, and therefore say that x squared dx minus dx gives us x squared minus 1 dx, just putting the bracket. Therefore, when you now do the integration with respect to x, having replaced z, you are going to get this term. And similarly, you can do the fourth term. You can do the fourth term. Having observed, first of all, that the fourth term says that the fourth term, or the fourth path, rather, the fourth path identifies, takes this shape from this point to this point. So what we observe here, what is constant is x. And you can see that x is equals to 1. X is not changing for path 4. And again, we can do it similarly and say that y and z, their changes are similar. And therefore, we can say that y is equals to z. Therefore, we can have dy is equals to dz. That is what we are observing at this point. Okay, that y is equals to z, and therefore dz is equal to dy. Therefore, we are going to be replacing dz with dy. So what we have is, again, I did the dot product, and I assume that you got how we are doing it, because the terms are going to follow just like we did for path 4. And since we do not have ax, this term is the one that we use. Therefore, you're going to have minus z dy and y squared dz. That gives you this term. And therefore, now once you have done that, you do this integration, it will give you 5/6. And therefore, the full line integral, which is a combination of the 4 terms, this is path 1, path 2, path 3, and path 4. It gives you the the closed path integral as minus 1/6. So that has been a bit lengthy, a bit detailed, but you can always refer to the notes or resume or run the video in case there's something that was not clear. I take another pause so that we can jump to the second section of the lecture today, which is lecture 5. Be sure that I am as clear as possible. I might have flashed through section 4 because I assume that you understood section 3, but that not being the case, I can show you section 4. Section 4 is right here. I rub all those and say the following, that section section 4 is this one. So the first thing we need to identify is what dimension is constant. And as you can see, along the x dimension, we are not moving towards that direction or towards that direction. Therefore, the x is constant, becomes 1. Number 2 is that both y and z are changing. And you can see their dimensions are equal in terms of this is equals to 1 and this is equals to 1. I'm trying to respond to Mr. Derek Ball as well. You can see that he's saying that he haven't understood why z is equals to x. In section 3, it is similar. So you can follow Derek to this one and you see that the ideas are same. So, so once you have identified this bit, you can actually say that y and z are equal because of their magnitude. And therefore, the change in y becomes the change in z. Having said that, therefore, we have no, this one is not part of that. We just know that dy is equal to dz. So we just come here now and say that for section 4, what we have said is that we identify the first thing as so x is equals to 1. And therefore, we replaced x in our equation with 1. And therefore, we end up with this, value of f being our vector. And then we are saying that dl, which is our elemental length, is equals to, it's changing in 3 dimensions, in only 2 dimensions, y and z, because we have said y remains constant, x remains constant. And therefore, this becomes my dl. Therefore, you just do the dot product. And the dot product says that you dot y component, ay component with ay component, and Z component with Z component. So you add up, this gets lost. And therefore, you are going to end up with Z dy, which is this term, Z or negative Z dy, and y squared dz, y squared dz. So these are the two terms you're going to end up with. Once you have got those two terms, and we have said that you can replace dz with dy, then you just pick one of them. Where there is z, you put y. So where there was z, you put y, and it becomes here. And where there was z, dz, you put dy. It becomes right there. So having said that, therefore you are able to do the integration as one-off without them being two. So you just factor out dy, you have y plus y squared, and there will be the negative outside. So once you do this integration, you simply end up with negative y squared over 2 plus y cubed over 3. And remember, our limits of integral were from 1 to 0. So I just put my 1 to 0 there. So when I replace y with 1 and 0 where it is supposed to be placed, then my answer becomes 5 over 6. So I have repeated that for the sake of Brian and Derek, and I hope that is clear. So we have said that the final integral gives us minus 1 over 6. Okay. Thank you. You say that is clear. So that is supposed now to allow us to progress to the section or lecture 5. And lecture 5 is a bit long. So what we have covered so far is that we have covered we covered that material. Last week we covered this. We apparently left this one. I never noticed that we have noticed. We've changed that. So that is what we have covered today. This volume, service charge, density, and line, they are going to be covered somewhere. So don't get worried about these ones. So, but what we've got to cover is that one. We are going to cover these things when we start on Kurops Law, etc. We have tried to do examples. So we have like combining lecture and the tutorial. So we have tried to